Well, hello and welcome to the first in the series of Absolute Beginners Electronics. I'm quite excited about this because this is going to be a series of very simple explanatory videos about the basic building blocks of electronics. But the important thing is it's aimed at people who know virtually nothing about it. So if you've got a fair bit of electronic knowledge or a bit of experience, this is probably not the video for you. I'm going to be talking about Ohm's Law today. I'm going to assume that you don't know what a volt is, that you don't know what an amp is, and that you don't know what an ohm is, except in maybe the most general, vague kind of ways. And I'm also going to assume you don't even know any very basic algebra. So I really am going to walk you through this step by step by step. The reason I want to do this is because although I ended up getting a degree in electronics eventually, I really struggled through school with basic maths concepts and basic physics concepts. It didn't come easy to me, and so I know what it's like when you don't quite understand something. So follow me now as we talk about Ohm's Law, and by the end of this video I promise you will understand it. Okay, sorry, this is going to be a little bit of chalk and talk, but that's really the only way to get basic concepts across. When we talk about Ohm's Law, I may as well just write it out for you, even though we're going to be dissecting this in great detail. It just says that the voltage is equal to the current times the resistance. Don't worry about any of that for the moment. We've stated it. Let's now talk about it. It involves three quantities: voltage, current, and resistance. We use V for voltage, we use I for current. I don't know why, it'll be some historical reason. You need to remember that I is current and R conveniently resistance. So we're okay with the V and the R, it's just the I is a little bit unusual. So it's a formula that relates voltage, current and resistance. Now why the heck do we even need to know about that? Well, the answer is that in all electronic circuits we usually have a source of voltage, in this case a battery, it could be any other source, and we usually want to drive some current round some kind of load. I suppose in the simplest example it could be a bulb like that, or more realistically in a circuit we will have a resistor like this, and the source of voltage simply drives current through the resistor and back to here. So if you like, electrons come out of here, they go through the resistor and they go back to there, forming a current, rather like a current of water. In the light bulb, the same thing. The electrons come out of here, go through one of the terminals of the light bulb, out of the other terminal of the light bulb, and back into the battery. So I think you can see there's nothing too difficult about the concepts of voltage, current and resistance. But I want to go just a little bit deeper than that, because, I mean, what is a volt? What is voltage? Not many people actually know the answer to this, and you will probably remember it from school. The fact is that like charges, negative and negative in this case, repel each other. We can have different charge, we can have a positive charge, but because they are like, in other words they are the same, they repel each other too. So a negative would repel a negative, and a positive would repel a positive. The only thing that attracts is opposite charges or unlike charges, positive and minus, and they attract each other. Just like a north and a south pole of a magnet attract each other, two north poles repel, two south poles repel. That's the only fact that you need to know. Voltage occurs when you try to cram negative charges together. It could be positive charges, but let's stick with negative. What do I mean by that? Well, supposing you have a negatively charged, let's call it a particle, an electron or whatever, and I try to bring up another one. We've got one over here, another negative one, and I try to bring it up to this one. Well, we know that negative charges repel each other. So as I get closer and closer and closer with this negative charge, I feel a stronger and stronger and stronger repulsive force. Again, think of forcing two north poles of the magnet together, and you just can't push them together if they're strong enough. Exactly the same thing happens for electrostatic charges. there comes a point where the repulsive force is quite strong. Now let's just say we can get it to stay here for some reason that I won't bore you with at the moment. Let's call it a chemical reason. This is a battery full of chemicals. It's the chemicals that allow these negative charges not to fly apart. Okay, we now have two negative charges, and we have a certain voltage here, by the way. Why don't we call it 2 volts? It isn't 2 volts, but let's call one negative charge 1 volt and another negative charge 2 volts, just to keep it kind of simple. So we've now got 2V there, 2 volts. Now I'm going to bring another negative charge up here. From here, I'm going to bring it into these two. Well, I've got 2 now. I've got 2 negative charges, and they're going to repel this even more strongly. So as I try to bring this negative charge up to here, I feel a stronger repulsive force than when I brought this one up, because I've got 2 there. But let's say I can get this chemically to stick here. You can see I've got a bigger repulsive force now because I've got 3 electrons there. Let's call it 3 volts. Now you know what I'm going to do. I'm going to bring up another negative charge from here. I'm going to try and bring that towards. Now I've got 3 pushing away, and I'm really feeling the force now as I bring this negative. It's getting quite hard for me to push this one up against these 3. Eventually I managed to do it though. It's taking ever more effort or work for me to bring this negative charge up, but now I end up with 4V. They don't fly apart because they're chemically bound. Just like I could bring 2 north poles of the magnet together like this, and if I nail them to the bench like that, they're going to stay there. I have kind of mechanically kept those north poles very close to each other. Well, we chemically keep the negative charges together in the battery or any source. So voltage is a measure of how many of these electrons are crammed into a smaller space. If I can get a lot of electrons into quite a small space, I can get a very high voltage. By voltage I mean repulsive force that will make these electrons want to fly apart. 2 electrons, pretty weak. If I let them go, this will meander away. If I've got 5 million electrons here and I let this one go, it'll really fly away quickly, because of the huge repulsive force between these 2 bodies. So this battery is nothing more than billions of negative charges all chemically crammed together so that they can't fly apart. But boy, oh boy, do they want to fly apart. If I were to give them half a chance, they would leap out of their chemical bonds and rush away. Where would they rush to? Well, they'd rush from this terminal here to this terminal here. If I were to put a piece of wire from there to there on this battery, that wire, relatively thin wire let's say, that wire would glow red hot. It'd be too hot for me to touch, even with this 1.5 volt battery, because the electrons would rush, freed from their chemical bonds, would rush away from each other and end up down at the lower energy stage. So that's what voltage is. It's charge crammed into a small space. Charge that wants to fly apart and get back down to a lower potential. Let's have a look at what current is. By the way, voltage was the difficult one. Current is easy. Why don't we connect a piece of wire to our battery here? I'm going to make it a fairly thick piece of wire, because I want to have a look inside this piece of wire. We're going to cut ourselves a window in this wire and have a little look inside here. Don't worry about signs, by the way. You know, is it electrons flowing down here, or is it positive charge flowing down? It doesn't really matter. If I now connect this positive to this negative with a piece of wire and I peer inside here, in theory with my microscope, I will see charges rushing past through this window like that. Billions upon billions of charges rushing past to end up down at this lower state here. And this is current flow. It's what we refer to as current. Very similar to water current. Maybe we'll do a little analogy in a moment with water towers and pipes and things. And now I am going to use a kind of water tower analogy. I'm going to talk about voltage in terms of height of water above the ground. This is our kind of girder. And we're going to put on top of here a tank. And I'm going to fill it with water. And I'm going to take a pipe out of here, and I'm going to take the pipe down to ground. Notice a lot of the terms we use in electronics are very kind of analogous. We talk about current, we talk about ground, we talk about resistance. Now our pipe comes down here. Let's make it fairly wide. And I think you can see that if we just let that run, the water will run out of here, it'll rush down here, and it'll come out of the pipe at the bottom. Okay, fair enough. So let's have a look now at our voltage, current and resistance. Well, voltage is the height of this tower. That's the analogy. The higher the tower, the faster the water will rush out. If we had a little shallow little dish here right on the ground, full of water, water would kind of just dribble out of there, wouldn't it? It would hardly come out. If I had a tank very, very high up, this is why we put water towers high, of course, because we want the water pressure. The water would come out much more forcibly, and by the time we got down to the bottom here, we'd have a real strong gush of water. So that's a good analogy for our electrons flying apart. Just a couple of electrons, we get a little dribble of water. A low voltage can't push very much. A low voltage, you can't do much work. You can't put a paddle wheel under here and get much power out of it. You can't get much power out of a low voltage. There aren't enough electrons to, and they move so weakly around. There's not very much repulsive force. So that's a very good analogy for voltage. Like all analogies, of course, it's not perfect. So here's our voltage on our water tower. Here's our current flowing. It just flows down here. It's the water flow. We can cut a window in here if we want to. We can actually stick a meter in there and measure the current flow there. Now resistance works out quite nicely in this analogy, because I think you can see if I put a resistance in this pipe by making it thinner at this point here, making it quite a little thin. Now suddenly what happens to the water? Well, the water goes down to very low pressure compared to when I had the full pipe width here. By putting a resistance in circuit, I have reduced the current for a given voltage. Ooh, that sounds quite useful. Let's just have a quick look at that. V equals IR, voltage is current times resistance. If I increase the resistance for the same voltage, then I have a decreased current. Don't worry if you don't get that, because I'm really going to walk you through that as well. I don't expect you to be able to rearrange that in your head and know about proportionality and that sort of thing. I promised you a beginner's series, and I'm going to give you that by explaining that to you as well. Supposing now I keep this resistance constant, I don't change that kink I've put in the pipe there, but I make the water tower higher. In other words, I increase my voltage. Well, now we've got, as you can see, more water pressure. Pressure is a very good analogy for voltage, by the way. And so our current will go up. We've increased the voltage, we've got more pressure, we've kept the resistance the same, but because we've got this higher water pressure, more current will flow down. Well, let's have a quick look at that. We've kept the resistance the same, we've increased the voltage, so the current must go up to retain this relationship. Again, don't worry, I'm going to walk you through this, but I hope you can see that quite clearly on there. I think that'll do for that. Let us now look at the actual equation V equals IR. We often want to know what's the current through a given resistance under a certain voltage. What's the current through a 10k resistor with 50 volts across it? What's the current through a 100 ohm resistor with 4 volts across it? We often want to be able to solve this equation. Now, to do that, we need to understand a little bit of basic algebra. Forgive me if this is so easy for you, you're yawning, but I did promise an absolute beginners series, and I'm going to stick with that because I remember I didn't get algebra when I was at school. I didn't understand it. Okay, let's look at this. V equals IR means V equals I times R. Just in case you didn't know that. It's just we don't like putting these little X's everywhere. It makes equations look very messy. You know, let's say that M equals Y times V times T times U. I mean, that's so messy. And so mathematicians just say M equals Y, V, T, U. They just forget the multiplication signs, particularly as we use X for equations, and then you've got these little X's and big X's. It's very confusing. So V equals IR means V equals I times R. We never actually ever put that in there. And we need to first of all look at the units that are used for voltage, current and resistance. Yes, what are the units? Well, I gave it away. Our unit of voltage is the volt, I believe named after Voltaire, who discovered it. Our unit of current is the amp, and I believe named after a Frenchman. Excuse me if any historians are here and screaming at the screen, but I think it was Ampere who coined the term amp. And you'll be pleased to know there's not a Mr. Henry resistance anywhere, but R is just for resistance, and it's such a useful term. We know what resistance means. You knew what it meant when I put it in the pipe. When I put a kink in the pipe, it's just anything that resists the current flow. So those are our units here, volts, amps and resistance. It's useful also to know that we can subdivide volts into bigger and smaller pieces of volts. So a volt is quite useful, but sometimes when you're looking at very small voltages, you don't want to be writing 0.0000157 of a volt. It all gets very messy. Just as if you're talking about big voltages, you don't want to be writing 157,000 million volts. It's very messy. So we have these units, which I'm sure you'll be familiar with. We have a millivolt. Milli is always 1,000th. A millimeter is 1,000th of a meter. So a millivolt is 1,000th of a volt. A microvolt is a millionth of a volt. Again, micro is always 1 millionth, no matter what you're putting that in front of. And now if you want bigger voltages, you can go for kilo. A kilo is always 1,000. A kilo is 1,000 grams. So a kilovolt is 1,000 volts. And then MV, a megavolt. Mega is always a million. So they're quite useful. Millivolts, microvolts for the smaller voltages, kilovolts and megavolts for the larger voltages. We never get involved in electronics. Kilovolts. We just don't get up to anything like this kind of level. We're always dealing in volts, millivolts, and probably not microvolts either. Amperes, exactly the same. We have a milliamp, which you now know is 1,000th of an amp. We have a microamp, it's a little mu, a Greek mu for micro. A millionth of an amp. I've never seen a kiloamp. I suppose there is such a thing. But that's 1,000 amps. We're getting up to kind of industrial level, national grid level amperages here. We don't ever get involved in any of these. And there's probably a mega amp too. I've certainly never got involved in any of this. Resistance, again, comes in the range. It's always measured in something called ohms. And this is named after another person, Ohm. I'm afraid I don't know his first name, and he was the one who came up with Ohm's Law and gave his name to the unit of resistance. Again, we can divide these up again, and common things are kilo ohms. Here's a little symbol for ohms. Look, you need to learn that. It's that little omega, I think it is. Kilo ohms is 1,000 ohms. And mega ohm, which is 1 million ohms. And we frequently come across resistances in these ranges. In fact, I'm just going to grab a couple of resistors for you now and show you. Right, I've just been to my resistor stash and pulled out 5 resistors. They'll all look pretty identical to you because the way we read resistors is by these little coloured bands on the body here, but I'm not going to do that now. I might do a separate video on how to read resistor colour codes. But I've just pulled out 5 resistors. This one is 100 ohms. This one is what's called 1K, 1 kilo ohm, 1K, and that's 1000 ohms. We talk about 1K resistors, 4K, 5K resistors, 6K resistors. That's how we speak about it in electronics, 6K. We don't say 6000 ohms. This is 10K, which means 10,000 ohms. This is 100K. These are all very common resistors that we use. 100,000 ohms. Mustn't forget my little omega. And this is a meg. We talk about 1 meg or 2 meg or 3 meg resistors. So 1 M, 1 meg we call it, which means 1 mega ohm, which is, as you know, a mega is always a million. So 1 million ohms. I want to just quickly mention one convention when we talk about resistors. We would refer to a resistor by its number of ohms or kilo ohms, which, as you know, is thousands of ohms. And typical resistor values are like 2.2K, 4.7K. But on circuit diagrams, on schematics, we don't tend to see 2.2K, 4.7K. And the reason is actually very simple. This little point gets lost. If you're on a schematic and you see 47K, you know, is that a 47K resistor, or is there a little tiny point in there that you can hardly see? So what we tend to do is go 2K2, 4K7, 6K8. And that means 2.2K, which, as you know, means 2,200 ohms, 4.7K, which is 4,700 ohms, 6.8K, which is 6,800 ohms. It's just a little convention. You might see this on schematics and think, what on earth does 2K2 mean? What does 4K7 mean? It means 2.2, 4.7, 6.8. Of course, if there's no point in there, in your value, you would write 68K would be 68,000 ohms, 47K, 47,000 ohms, 220K. There's no decimal point here, so we just stick the K on the end. 220,000 ohms. It's only if there's a decimal point do we put this K in the middle here. Just a bit of a weird convention. Formula again, V equals IR, which, as you remember, means I times R, I multiplied by R. And see how we can use this to find out any one of these terms if we know the other two. So if we know current and resistance in the circuit, we can tell the voltage just by plugging in the numbers here. If we know the voltage and the resistance, we can determine the current. If we know the voltage and the current, we can determine the resistance. There's nothing mysterious about this. I promise to walk you through this as an absolute beginner, and so I will. 6 equals 2 times 3, I think you'll agree. Well, if we didn't know 3, didn't know what that was, 6 equals 2 times something. Well, we know 6 and we know the 2. What's the third thing? Well, 6 equals 2 times something, 6 equals 2 times 3. We can work out what the something is. Similarly, let's say we don't know what this is. So 6 equals something times 3. Well, we know 2 of the terms. Look, we know the voltage is 6, we know the resistance is 3. We can find out the current because something times 3 equals 6. Well, something is 2. So we would know that the current is 2 in this case. So I hope you agree that that's, if we know 2 of these terms, we can find out the third one. So the only difficulty now is rearranging V equals IR to find the unknown term. It's fine if we want the voltage and we know the current and the resistance, well, that's simple. We just plug the number in there, plug the number in there, multiply them together, and out comes V. But suppose we want the resistance, knowing the voltage and the current. Well, that's not quite so easy. We need to get rid of this I here. So let's just write that again. V equals I R. Remember, I times R. We know the voltage and the current, and we want the resistance. So we want R equals something. We don't want this messed up with the I. So we need to kind of get rid of the I here. Well, you may remember from your school mathematics that any term on this side you can take under here. In other words, you can get rid of the I there and put it under here. So V upon I equals R. So now we've got R equals something. We can plug in V, we can plug in I, and out comes R. Again, there's nothing mysterious about this. Look, 10 equals 2 times 5. I want to know what 5 is. In other words, I want to get rid of the 2 here. I want 5 equals something. And to get 5 equals something, I've got to get rid of this 2. Well, how do I do that? I take the 2 underneath here and get rid of it here. 5 equals 10 divided by 2. Well, that was fairly simple. And there's nothing mysterious about taking this term here and putting it under here. It's not some kind of magic trick. Let's do this again. 10 equals 2 times 5. Agreed? I'm putting the times in because otherwise it looks like 10 equals 25. So 10 equals 2 times 5. I want 5 equals something. How do I get rid of that 2? Well, I could divide this side of the equation by 2. 2 upon 2 is 1. So you might remember we kind of cancel these out. So 2 upon 2 is 1. Anything upon anything is 1. 5 upon 5 is 1. 100 upon 100 is 1. 1 times 5 is 5. So we can cancel this 2 here. But hang on, we can't just do something to one side of an equation without doing it to the other. We divided this side of the equation by 2. We must divide that side of the equation by 2. We can't just haphazardly do something to one side. So 5 equals 10 upon 2. And the shorthand is we took this 2 here, which was on the top here, and put it down underneath here. That's the shorthand way of doing it. But expanded, that's what's really going on. Okay, so now we're in a position to solve, if you like, V equals IR for any term. V equals IR. Well, what does I equal? Well, if we want I equals something, we've got to get rid of the R from this side. It's extremely inconvenient having that. So we will divide by R. R upon R is 1. Anything upon anything is 1 if it's the same term. We had to divide this side by R as well. We divided that side by R. We must divide that side. Sorry, it's a bit cramped here. I'll redo that. So I equals V upon R. Or putting it another way, a simpler way, we wanted to get rid of the R. We take it down underneath here and get rid of it from that side. I equals V over R. I equals V over R. So if you know the voltage and the resistance but want to know the current, that's the formula you use. Let's do the same for R. In other words, we don't know what R is and we want to know. We want R equals something. We don't want it messed up with this I here. Well, you now know that we can take this I down underneath here, get rid of it from that side of the equation, put it down under here. R equals V upon I. And there you have the 3, and there are only 3 permutations of the equation. We have V equals IR, we have I equals V upon R, and we have R equals V upon I. Let's just kind of intuitively check whether this feels right to us. For a given voltage, if I increase the resistance, what happens to the current? Well, the current goes down. Let me prove it to you. Let's say the voltage is 10, resistance is 2, 10 upon 2 is 5, we have 5 amps. I'm going to increase the resistance. I'm going to make it 5 ohms. Well, I've increased the resistance, the current goes down. Remember our water pipe, the current went down. 10 upon 5 is now 2. So increasing the resistance decreases the current. So this kind of feels right, this equation. Let's have a look at this one. What happens to the resistance if I change these values here? So let's say 10 volts upon 2 amps, the resistance is 5 ohms. Must be 5 ohms. If I've got 10 volts and 2 amps flowing through a resistor, the resistor must be 5 ohms. Supposing I increase the current, let's make it 5 amps. 10 upon 5 amps. Well, the only way I can possibly do that is if the resistance goes down now to 2 ohms. So again, that kind of feels right. Lower resistance, more current, or more current, it must be a lower resistance. That kind of feels right too. So all that remains for us to do is a couple of little practical examples. I'm just going to write on top of here the 3 equations. R equals V upon I. Those are the 3 equations, depending which unknown we want, whether we want to know the voltage, the current, or the resistor. And let's just do a practical circuit. So let's say we have a 10 volt battery. And we have a 1K resistor. There we go, is our 1K, which if you remember is 1000 ohms. What is the current flowing through that resistor? Well, as soon as we say what is the current, that means we don't know what the current is, and we need this equation here. We need I equals something. Well, we know what it is, it's V upon R. V is 10 volts, let's plug in some numbers here. So our unknown current is 10 volts upon our resistor. Remember, our resistor is always in ohms. 1K is 1000 ohms, so 1000. 10 upon 1000 is 1 upon 100. So our current is 1/100th of an amp, which is 0.01 of an amp. We would put this in milliamps because it's much less of an amp than 1 amp. It's 100th of an amp. So I'm sure you know that to make something into milliamps, you have to move this decimal point 3 places. So we would go 1, 2, 3, and that would be 10 milliamps, or 10 thousandths of an amp, or 1/100th of an amp. Agreed? We can do the same again now, supposing we wanted to find out the resistance, having measured the current. So let's say we have a, let's keep our battery at 10 volts, and we have some kind of unknown resistor here. We just don't know what that is, but we measure the current here at let's say 0.02 of an amp, which is 20 milliamps. We measure 20 milliamps current. How do we do that? We just stick a meter in the circuit, break the wire and stick a meter in the circuit. What is the resistance? Well, when we say what is the resistance, we know that the unknown is R. R equals V upon I. Plug in some numbers and turn the handle. V, what's V? 10. We can do that, that's easy. What's I? Remember, it's always in amps. We don't write 20 for milliamps, it's always in amps. So it's 0.02 of an amp. You could use a calculator to do this, or quite simply, we want to get rid of this awkward decimal, so let's multiply the bottom by 100, make it 2. Multiply the top by 100, make it 1000, so it's 1000 over 2, which is 500. So it's 500 ohms. Not very surprising actually when you look, because look, we've got double the current going through the circuit we had here with a 1K resistor. Voltage is the same, current's double, resistor must be half. Just like the water tower height's the same, the current going through the pipe is double. Well, our kink in the pipe must be twice as wide, if you know what I mean, using the analogy there. I suppose we ought to just be, for the sake of completeness, let's do the simple case V equals IR. So in other words, we want to know what's the voltage of this battery or power supply, doesn't really matter. What is this voltage here? If I measure 1 amp, quite a high current that, going through a 10 ohm resistor. Well, the unknown is V, so V equals IR. We just plug in some numbers. I is 1 amps, correct, times 10 ohms, correct, 10. 1 times 10 is 10, 10 volts. We can solve for anything we want here. So let's now have a look at a practical circuit, which is the sort of thing you might see in a valve amplifier. So here is a valve, there's the grid, here's the plate, here is the plate resistor, and let's say this goes up to an HT of 300 volts. Don't worry about that plate resistor value at the moment. We're interested in the cathode resistor, which is this one here, and this goes down to ground. Let's assume that this is a 4K7 resistor. Remember, that's 4.7K, which is 4,700 ohms. A very typical value resistor, by the way. And let's say we measure 10 milliamps through the valve. 10 milliamps, if you remember, is 10 thousandths of an amp. What is this voltage here? What's the voltage across this cathode resistor? Quite a useful thing to know. Well, to do that we use Ohm's Law, V equals IR, plug in some numbers, making sure we get our units right. So I is 10 milliamps, or 0.01 of an amp, multiplied by the resistor, which is 4,700 ohms. 0.01 times 4,700 is 47 volts. If you found that hard, ask yourself what 1/100th of 4,700 is, and you'll get 47 out of that. Or we move the decimal point 2 places to produce 47 volts. So, looked at another way, supposing we wanted to know what current's going through this preamp valve. Well, we measure across the cathode resistor, and let's say we measure 47 volts, and we know it's a 4K7 resistor. We would say, there's 10 milliamps going through this preamp valve. So there you go, that's the practical application of Ohm's Law. Okay, I'm going to try a crazy quick demonstration here, which may not work. It's a little bit messy here on the bench. But what I've got here is a 9 volt nominally battery, although it's a bit flat. And I'm going to load it with a resistor, so it's going to go even flatter. And I've got a 470 ohm resistor here. So what I'm going to do is I'm just going to connect that 470 ohm resistor straight across the 9 volt battery, and then I'm going to measure the voltage of the battery, because we want to know V, which is the battery under load. That's why I'm not measuring it. Now it's going to be less than 9 volts. Now I'm going to measure across there, and it's 6.5 volts. I'm going to disconnect that because that is flattening the battery quite a lot. So let's just make a little note of that for ourselves. 6.5 volts. Now I'm going to do exactly the same thing, but I'm going to put the meter in series with the resistor and measure the current. To do that I need to move this over to the milliamps, turn this to milliamps. So now when I put these probes on, I'll be measuring the current through the resistor. So let's see what that is. Hopefully this will work. 14.2 milliamps. Okay, let's make a note of that. We can move all this now out of the way. 14.2 milliamps is what we want to remember. So we had 6.5 volts and 14.2 milliamps, and if you remember we had a 470 ohm resistor. Let's see if this actually works. Here's the circuit. I'm sure you don't need me to draw this, but basically this is where we put our ammeter measuring the current. Here's our 470 ohm resistor, and this is going back round here. And we measured the voltage across here with the meter. Let's plug these numbers into Ohm's law and see if they come out. They won't come out exactly right, but let's see if it kind of works. So volts, amps and ohms. We need to be a little bit careful with our units here. Remember, V equals IR. V's easy, that's 6.5 volts. Let's be a little bit careful with the current. It's always in amps. We've got milliamps, so we need to go 1, 2, 3, 0.0142 amps. 1, 2, 3, 14.2 milliamps. Check. Multiplied by the resistance, which is again straightforward, 470 ohms. That should work out that equation. So let's see if that times that is about 6.5. 0.0142 times 470, let's see if we get lucky, 6.6 volts, which is very close to the 6.5. The reason it's not spot on is because we weren't very accurate measuring these voltages and currents, and every time I put that resistor across that rather flat battery, the voltage is going down and down and down as the battery is discharging. So there we are, perfect demonstration of Ohm's law. We've got our 6.6, 6.5, close enough. That's how it works. Well, there you go. That's Ohm's law for you. There are tons of videos on YouTube about Ohm's law. I didn't want to just duplicate those. I wanted to take it from the absolute beginner's perspective and drill right down into the detail. I hope I didn't go too slowly for you, and I hope you weren't groaning in frustration, but this is an absolute beginner's series. I hope you enjoyed it. I hope to do a few more of these, and I'll catch you on the next video.